A lot of discussion about the habitability of exoplanets focuses around the habitable zone surrounding a star. This refers to the distance at which starlight is adequate to heat the surface of a planet sufficiently that liquid water can exist at the interface between the crust and the atmosphere. However, many astrobiologists have proposed mechanisms by which life could exist out past the orbit of Mars, or the frost line. At this distance, the ambient temperature in space was low enough for volatiles like water and ammonia to form solid grains. As a result, planetary bodies this far out have a frozen, uninhabitable surface, but may have liquid water deep down, which is heated geothermally and could harbor life. The most commonly discussed planetary bodies in this regard are Jupiter's moon Europa and Saturn's moon Enceladus. Saturn's other moon Titan and Neptune's moon Triton have also been subjects of interest, but if life is present there, it would have to have a biochemistry quite different from ours. Europa is the smallest of the 4 Galilean moons, and the second closest to Jupiter after Io. Io is famously a volcanic world as a result of tidal heating produced by its tight orbit around Jupiter. Europa, being further out, isn't subjected to sufficient tidal heating to result in kilometer-high volcanoes, but it can keep liquid water beneath its icy crust. Although, it's now believed that the other Galilean moons play a role in the tidal heating of Europa as well. It's estimated that the crust is between 15 and 25 kilometers thick, while the ocean underneath is between 60 and 150 kilometers deep. For some perspective, the average depth of the world's oceans is 3.6 kilometers, while the deepest point, the Mariana Trench, is 10.9 kilometers deep. This means that the pressure at the average depth of the world's oceans is 35.2 megapascals, while at the bottom of the Mariana Trench it's 107 megapascals. With the acceleration due to gravity on Europa being 1.315 meters per second squared, at the lower depth estimates, the pressure on the bottom of the subsurface ocean would be 99 megapascals, and at the greater depth estimates, it would be 230 megapascals. Meanwhile, the pressure directly under the icy crust will be between 19.7 and 32.9 megapascals. At all of these pressures, water exists as a liquid at temperatures between 0 and 100 degrees Celsius. But the key question here is, could life survive and grow under these conditions? A bacteria, known as Calwellia marmemaniae, which was isolated from the deepest part of the Mariana Trench, has been shown to be capable of growing at 140 megapascals. Theoretical calculations have indicated that microorganisms should be able to grow at pressures as high as 150 megapascals. So, if this is indeed the limit, life would not be able to grow at the bottom of Europa's subsurface ocean with the deeper depth estimates, but would be able to grow at the shallower ones. But either way, at least some of it will be habitable. So, what kind of life could live down there? Many have cited deep-sea hydrothermal vents as a possible oasis of life in Europa. On Earth, we have similar habitats at the bottom of the sea. It's commonly claimed that down there, communities exist independently of the sun, with chemolithotrophic bacteria forming the base of the food chain. However, this statement is only half true, and I say half because the chemolithotrophic bacteria power their metabolism by reacting ferrous iron and sulfites in the vent with oxygen in the water column, forming sulfate and ferric iron. While the iron and sulfites came from the magma beneath the vent, the oxygen was produced by photosynthetic organisms near the surface, who are of course powered by sunlight. Now, there are some hydrothermal communities like those in the deep crust, which do exist completely independently of the sun. The microbes down here do so by reacting sulfite, which is formed by reactions between volcanogenic sulfur dioxide and water, with hydrogen, which was also released from the magma. What does this mean for the habitability of Europa? Well, Even though light couldn't penetrate its icy shell to enable photosynthesis, Europa lies within Jupiter's radiation belts. Here, the magnetic field traps ionized particles from the solar wind, and these will strike water molecules in the crust, producing hydrogen and oxygen. The lighter hydrogen flies off into space, while Europa does have a thin atmosphere of oxygen. It's estimated that 1,000 tons of oxygen are produced per day on the surface of Europa, and a lot of this will percolate through the icy crust down to the subsurface ocean. For comparison, the total photosynthesis on the Earth produces 1.5 billion tons of oxygen per day. How much chemotrophic primary productivity could this much oxygen sustain? On Earth, roughly 10 to the 17th grams of carbon are fixed by primary producers globally each year, while 1.4 times 10 to the 12th grams are fixed by deep-sea microbes inhabiting hydrothermal vents. In order to produce organic carbon, deep-sea microbes use the electrons from sulfides to reduce carbon, but since sulfur is more electronegative than carbon, an input of energy is needed to do this. They utilize a cross-membrane pH gradient to reverse the respiratory complex 1's reaction. In our cells, it oxidizes NADH, reduces quinones, and uses the energy from the reaction to pump protons against the concentration gradient. Meanwhile, sulfur oxidizers oxidize sulfides using a quinone as the electron acceptor, and use the influx of protons from a high to low concentration to drive the oxidation of quinones, a more electronegative compound, by NADPH, a less electronegative compound. This then shuttles the electrons to the Calvin cycle, where they fix carbon. This cross-membrane gradient is produced by the oxidation of sulfides, where the flow of electrons from them to the oxygen is used to pump protons against the concentration gradient. As such, more sulfides will have to be metabolized per carbon assimilated. How much? Well, the difference in half reduction potential of water and oxygen and sulfides and sulfate is 982 millivolts, while that between sulfides and sulfate and bicarbonate and acetate is 113. Given that biotic energy conversion efficiency is about 50%, oxidizing one sulfide with oxygen should provide enough energy to oxidize 8.7 carbon atoms with electrons from sulfide. As such, few of the sulfides metabolized would be needed to reduce carbon, but assimilation requires more than reduction. The carbon also has to be assembled into biomolecules, and this process requires energy. How much? Well, marine heterotrophic aerobic bacteria usually assimilate around 25% of the organic matter they consume, while oxidizing the remainder to power their energy metabolism. Sulfur oxidation will yield 90% as much energy per electron as carbon oxidation, but when sulfide will yield around 8 electrons, while most carbon atoms in the form of organic matter will yield 4. This gives a ballpark estimate of 1.8 sulfides per carbon assimilated, which we can round off to 2 when we account for the added energy needed to reduce carbon. 2 oxygen molecules are needed to oxidize each sulfide to sulfate, so sulfur-based primary productivity in the dark will require 4 oxygen molecules per carbon atom assimilated. When we normalize for the fact that the oceans cover 70% of the world's surface, we get that 1/100,000th of the primary productivity in the oceans is chemolithotrophic, and since each carbon atom fixed by phototrophy produces 1 oxygen molecule, and each carbon atom fixed by chemotrophy uses 4, 1/25,000th of the oxygen produced is needed to sustain the Earth's deep-sea hydrothermal communities. With the surface area of Europa being about 1/10 that of the world's oceans, we get that oxygen production on Europa per unit area is 1/150,000th of what it is on Earth, i.e., it couldn't support comparable levels of primary productivity as the bottom of the sea on Earth. Meanwhile, the total high-temperature hydrothermal heat flux on Earth is 3 times 10 to the 11th watts, and that on Europa is at least 5 times 10 to the 11th watts. Given the surface area of Europa is 6% that of the Earth, the hydrothermal heat flux, and in all likelihood reduced volcanic gases emitted per unit area, will be roughly 28 times that of the Earth. As a result, if chemolithotrophic primary productivity is present on Europa, it will likely be oxygen limited. Although, I should add the caveat that there are a lot of estimates as to how much oxygen is produced on Europa, with some estimates going as high as 1 ton per second, or 86,400 tons per day, in which case it could support greater levels of primary productivity per unit area than the deep sea of the Earth. If we assume the upper limits for oxygen production, the oxygen is still the limiting factor, with there being twice as many reductants as the oxygen available could oxidize. So, if there is indeed microbial life on Europa, it would probably also have a mostly anoxic ocean. This is in a way disappointing, because the revelation that oxygen is produced on Europa opened the possibility that apart from microbial life, it could harbor animal-like organisms, and these could form communities reminiscent of those we find around deep-sea vents. But with most, especially the deepest part of the ocean being anoxic, this is highly unlikely. Although, the notion of animal-like organisms living in Europa's ocean may not be completely dead in the water. Oxygen influx would be greatest near the surface, while the influx of reduced gases would come from below, so you could have had zones of oxic water near the bottom of the icy crust. This possibility is exacerbated by the fact that the turnover rate of Europa's oceans is about 1/100th that of the Earth's, preventing homogenization. Also, the subglacial layer would get more meltwater from the crust, decreasing its density, while the water from the deep will be enriched in briny hydrothermal fluids. This can result in the formation of haloclines, or where differences in density limit the mixing of the water between the two zones. This halocline would also represent a chemocline, with an oxidizing layer above and a reducing layer below. At the interphase, microorganisms could oxidize various hydrothermally emitted chemicals such as the aforementioned sulfides, forming a chemoplankton. Meanwhile, small microscopic animal-like aliens could eat the chemoplankton, and these would be Europa's version of zooplankton. These could in turn sustain larger fish or squid-like aliens, giving rise to a food web. Although, with rates of primary productivity being lower than they are on the Earth, it probably wouldn't have as many trophic levels, making the idea of whale-sized creatures living beneath the icy shell unlikely. In a way, this subglacial zone could be seen as an upside-down ocean, with the chemocline beneath the animal-like organisms being reminiscent of the surface, and the ice above acting like the seabed. On Earth, there are subsurface brine lakes where hypersaline water comes up from below and pools on the bottom. Here, the halocline resembles the surface of a body of water on land. Upon death, some of these organisms would sink into the anoxic zone. There, instead of oxidizing their constituent organic carbon, microbes could ferment their remains, generating energy by breaking down their complex biomolecules into simpler organic ones. These organic molecules would then be made part of the pool of reduced compounds in the anoxic zone, which could then be oxidized by the chemoplankton at the halocline. In the deeper parts of the ocean, microbes could make a living by other means. Europa's mantle is likely more reducing than Earth's due to its smaller size. This is because the higher gravity at the core mantle boundary results in more of the denser zero-valent iron going into the core, while the less dense ferric iron goes into the mantle. So, there would be more hydrogen emitted by volcanic vents, and this could be oxidized by microbes using carbon dioxide that also would be emitted, producing methane. Meanwhile, in the icy shell, some of the water would seep up into the cracks, and although most of the reduced compounds would be in the deep zone, some would diffuse up into the crust. At the highest places water could seep up, some of the hydrogen that didn't get blown off into space would be present. It's been shown that here on Earth, microbes in desolate environments can sustain their growth by oxidizing trace gases, which make up minor constituents of the ambient atmosphere, most notably methane, hydrogen, and carbon monoxide, and some of these live in the ocean. As such, microbes inhabiting the crevices of Europa's crust could make a living in a similar way, oxidizing either trace amounts of reduced compounds that were released from volcanic vents deep below, or hydrogen produced above by splitting water. Perhaps microbial communities which inhabit subglacial lakes and glacial cavities filled with water in Greenland and Antarctica can provide insight into how similar communities would function on Europa. Glacial pore water communities are often dominated by a single microbial taxa, such as Polaramonas, implying if such communities existed in Europa's crust, they'd be low diversity. When we look at the surface of Europa, we see little cratering, implying the surface is between 40 and 90 million years old. Furthermore, the Hubble telescope has detected geysers coming from the surface of Europa. So, it appears that the Moon is tectonically active, with probes sending back images of the surface with large pieces reminiscent of the tectonic plates on Earth. In some places, water comes up from below, forming new crust, while in other places, subduction happens, and the crust goes down into the ocean where it melts. In various places on the surface, such as on the fault lines, we see brownish-green coloration. This is believed to have come from organic material which seeped to the surface from below. Once there, it was quote-unquote cooked by ionized particles in Jupiter's radiation belts, forming an odd and quite random assortment of organic molecules. If a probe was to land on Europa's surface, perhaps it could find remains of biomolecules from subsurface organisms in these colorful streaks. Another one of Jupiter's moons, Ganymede, is said to have a subsurface ocean. At 100 kilometers, this one is estimated to be about as deep as Europa's, and it's buried beneath a 150-kilometer thick ice crust. With Ganymede's surface gravity being 1.428 meters per second squared, this puts the pressure at the base of the ice crust at 214 megapascals. If the aforementioned 150 megapascal limit for microbial growth is accurate, the pressures in Ganymede's subsurface ocean would render it inhospitable for life. Although, the water would be liquid all the way from the top to the bottom of the ocean, so if 150 pascals isn't the limit, then perhaps life is possible on Ganymede as well. Furthermore, Ganymede has two types of surface terrain, the older, darker, cratered variety, and the younger and lighter terrain with many fault lines. The darker terrain is estimated to be in excess of 4 billion years old, while the age of the lighter terrain is not well constrained. But it does suggest that water is seeping up into the crust. In this pore water, pressures would fall in the range we know life can grow under, possibly forming microbial oases. How would they make a living? Well, one possibility is that they could react reduced trace gases like hydrogen and methane with trace oxidized ones like carbon dioxide and sulfur dioxide, all of which would have come from deep below in the mantle. But how could these microbes disperse from one pocket to the other? Even if microorganisms can't grow in pressures in excess of 150 megapascals, they can survive as dormant spores in pressures in excess of 1 gigapascal. So, after growth and division occurred in one of these pockets, some of the organisms would fall back down into the subsurface ocean where they go dormant, get washed around, and, the next time an upwelling occurred, some would be moved up into another pocket where they grow and divide and the cycle repeats. Although, with the division rates in these pockets being very low, and the odds of an organism which fell into the subsurface ocean ending up in a new pocket being quite slim, it's probably unlikely that any organism which came into being in one of these pockets will find another one before it closes up. So, I'd argue that life on Ganymede is pretty unlikely. Going out further in the solar system at Saturn's orbit, we find Enceladus, which, at 500 kilometers in diameter, is the second smallest of Saturn's major moons and the second closest to Saturn. Like Europa, it's subjected to tidal heating due to its close proximity to Saturn. The Cassini probe saw geysers erupting from the south pole of Enceladus, implying a liquid water layer is present below the icy crust. The total thickness of the surface water, both the ice and liquid, is estimated at 100 kilometers, and with the acceleration due to gravity on Enceladus being 0.47 meters per second squared, the pressure at the bottom of the ocean will be 47 megapascals, well within the range microorganisms are known to grow in. The resurfacing rate on Enceladus is even greater than Europa, with much of the crust estimated to be around 5 million years old. INMS and UV-Vis aboard the probe detected molecular nitrogen, carbon dioxide, methane, propane, carbon monoxide, methanol, hydrogen, and cyanide in the plumes emanating from the geyser. This means that if organisms are present in the subsurface ocean, they could react hydrogen with carbon dioxide or carbon monoxide, producing methane as a means of producing energy. They could also uptake organic molecules in intermediate redox states from the environment, such as formic acid, formaldehyde, methanol, and cyanide, to be assimilated into their biomass, since these have an elemental stoichiometry more similar to organic matter. While organisms could live on moons such as Europa and Enceladus, in order for a planetary body to be inhabited, it not only has to have conditions conducive for the continuation of life, but at some point it had to have conditions suited to its origin as well. It had long been hypothesized that life had begun in a deep-sea hydrothermal system, given that ancestral state reconstructions of all organisms alive today indicate that their ancestor likely lived in a similar habitat. However, this approach, often referred to as the top-down approach, can inform us about the last common ancestor of everything alive today versus what the first organism was like. The more we study prebiotic chemistry, the more the importance of hot-cold, wet-dry, and acidic-basic cycles are elucidated. However, there are two important caveats. First, just because life on Earth didn't begin in a deep-sea vent doesn't mean a separate variety of life with a different biochemistry couldn't do so. Second, some prebiotic processes are known to be driven by freezing-thawing cycles, such as the polymerization of RNA nucleotides, which would occur in the crust of Europa and Enceladus. So, these could act as a substitute for the wet-dry cycles, and life could begin in their crust. One problem with this idea is that other prebiotic cycles, such as the abiotic analog of the TCA cycle used to produce amino acids, are catalyzed by solid minerals. However, asteroid impacts could deposit such minerals in the icy crust of Europa and Enceladus when the solar system was young, and thus provide the necessary catalytic surfaces. Even if life couldn't begin on such icy bodies, there is still the possibility that life arrived there, carried on impact ejecta from Earth, or possibly Mars. While such an impact probably couldn't completely penetrate the crust, it could deliver organisms to smaller bodies of water within the crust, which would then find their way into the subsurface ocean. While icy bodies in the outer solar system may be inhabited, how could we identify the presence of life on them? Some have argued that we should send a surface lander, which would then either drill or melt its way through the crust. Once this is done, it can release a submersible probe to explore the subsurface ocean. This may take some time, but one way to make it go faster is to have an earlier probe take seismic measurements and identify locations where liquid water is penetrating into the crust. This way, a later surface lander would only have to melt its way through a few kilometers of ice, and the submersible probe would then swim through the crevice and into the ocean. Apart from Enceladus, Titan, Saturn's largest moon, has been identified as a potential location life can live. Titan is the only moon with a thick atmosphere, which has a surface pressure 1.5 times that of the Earth, and the only other terrestrial body with liquid on its surface besides Earth. The atmosphere of Titan is composed mostly of nitrogen, and instead of water, the liquid on its surface is methane and ethane. Furthermore, in both the atmosphere and on the surface of Titan, there are a wide variety of organic molecules present, i.e., the building blocks of life, which is why it's very tempting to speculate about the possibility of life there. However, if it is present, its fundamental chemistry would have to be very different from life on Earth, because unlike water, methane and ethane are nonpolar. How biochemistry would function if it occurred in a hydrocarbon solvent is a topic for another time, and I'm currently working on a video about alternative biochemistry while writing this one. So, keep an eye out for it if it's not out by the time this video is uploaded. However, if it is possible for biochemistry to function in a nonpolar solvent, the surface temperature of Titan is on average negative 183 degrees Celsius, which is probably too low to initiate prebiotic chemistry. Some have argued that while not habitable now, billions of years in the future, the Sun will swell up, becoming a red giant, at which point Saturn will be in the habitable zone. At this point, liquid water will exist on the surface of Titan, which would have come from its icy crust, and it could host prebiotic chemistry with the abundance of organic molecules that are on the Moon now. But one problem with this idea is that this ocean would have high levels of ammonia, and thus be too basic for life to begin, deprotonating too many functional groups for metabolic reactions to be viable. Going out all the way to the orbit of Neptune, we find its largest moon, Triton. This moon is unique in that it is the only major moon with a retrograde orbit, revolving opposite the direction Neptune rotates. Despite having the coldest surface temperature of any known body in the solar system, Triton has an atmosphere which, while having only 1/70,000th the surface pressure of the Earth's atmosphere, is known to host thin clouds. Both the gas of the atmosphere and the icy clouds are made mostly of diatomic nitrogen. Much of the surface of Triton is covered in lightly cratered and heavily ridged cantaloupe terrain, which is less than 10 million years old, implying recent resurfacing. Furthermore, geysers of nitrogen frost have been detected near the South Pole, and these deposit streaks on the surface. These streaks are believed to be tholins, or organic matter cooked by radiation. This, coupled with the young age of the surface, strongly suggests there is liquid flowing through Triton's icy crust, which heats, melts, and sublimates bits of frozen nitrogen in the crust, resulting in the geysers. This can be seen as an analog of magma heating subsurface water which erupts as a geyser here on Earth. The presence of tholins in the geyser streaks also means this liquid has organic matter in it. All of this in turn suggests the presence of a subsurface ocean, but other explanations for the aforementioned observations haven't been ruled out. Given the abundance of ammonia in the crust of planetary bodies in the outer solar system, it's likely that if an ocean is present, it would have high levels of ammonia as well. So, if life is present there, it probably would again have to have a fundamentally different biochemistry from ours. Although, exactly how much ammonia is in the outer layer of Triton is not well constrained, so if present in relatively low concentrations, it would result in any subsurface ocean having a basic pH. There are organisms known as alkalophiles which thrive in basic environments and grow in pHs as high as 11.5. As such, the presence of ammonia may not rule out the possibility of organisms with a biochemistry similar to those on Earth living on Triton. But how could such organisms make a living? Given that we aren't sure that Triton even hosts a subsurface ocean in the first place, pretty much nothing is known about its chemistry apart from it having ammonia and some organic molecules, so it's pretty much pointless to speculate on this matter. If we find life out this far 100 or so years in the future, it will be a monumental find that will undercut many assumptions we had about planetary habitability. Such a discovery on Triton, or Enceladus, or Europa will inform us that life isn't restricted to what we have long considered to be the habitable zone, and instead can be present in the deepest, darkest, and coldest reaches of space. Thanks for watching, and as always, if you enjoyed what you saw, please like and subscribe.